Today we will continue with PA2, the foundations, principles, ideas, concepts, all the things, all the good stuff. Okay. So thank you very much, Satya, for coming also, and Aruna. Let's make today a very effective day. All right, I'm going to open up the PA2 node PowerPoint deck. Where is PA2? This guy, full notes. Okay. So in between, if I try to catch up my breath, please have some patience. It's good to connect with you, but the downside is I'm not really 100% what I used to be. Okay. All right. So quickly, let me review these things. Are you ready?
Yes, sir.
Cool, very cool. All right, so matrices are fundamentals. Did I start? Am I recording? Yes, recording. Matrices are fundamental. It is capturing the weights for linear relationships. That's what matrices does. See here, these are all the weights for linear relationships among X, Y, Z. And these weights matter in life for all kinds of problems. Okay. And when given some weights, we can solve for these unknowns. You know what values it will be, so that the product of this times this is equal to 6. The product of this times this is equal to -4. The product sum of this and this is 27. So that's a fundamental structure of matrices, and we approach from the point of view of solutions of equations, and that provides the mathematics for reducing the dimensions of big data. Okay. That is the purpose. Matrices provides ability to reduce the big dimension to manageable dimension. So once you have a matrix, and even in this case you can see, we need to define what is called an inverse inverse concept, and that's what A inverse means. Okay. And matrices in graphics helps you to achieve these things digitally. You are not redrawing this M like this. You are just using a matrix to scale it like this. You are not redrawing this into this. You are using matrix to rotate this like this. Digitally it is done. So you just plot those points, it comes out to be like this. That is a matrix that transforms this to this. You are not actually, your machine is not actually drawing this. The mathematics, the matrix, helps you identify these points, skewed points for a given matrix that is pre-multiplying this. Okay. Very important. And then I give you all these notes. I talked about the importance of inverse and how do we get inverse through row operations. Okay, that's very important to know that, because unless you have that confidence, you'll have difficulty pursuing lots of other concepts we continue to do. And one of the important concepts is how do we use matrices to expand the results of linear regression for 2 variables. Are you with me, you guys?
Yes, sir.
Okay. You are able to hear me well, right?
Yeah.
Yes, sir.
Okay, cool. Thank you. So I walked you through how matrices are very nicely utilized to solve a regression problem of any number of variables. So beta can, the y is n observations, the number of variables are, let's say, k variables. So beta is a vector of size k, and beta is solved with this formula, and we derive that purely as mathematical derivation. Very powerful mathematics. Mathematics is, with mathematics you can move to finite dimensions to even infinite dimensions. Okay, so anyway, now from there, as a second application, I'm seeing this. Probably I am overselling it. Don't be careful about that. Also, I'm not overselling it, but every time when I speak, I'll be giving you a different angle. So this time probably I'm because I'm trying to condense the review, I will review it from the point of view of matrices. But that doesn't mean that I'm trying to. That doesn't mean that this class is about matrices. It's really about big data. Okay. So and then the next one I talked about what is meant by map. Hello.
Yes, sir.
Okay. Our next topic I introduced was how do we. What does that mean? Not how do we. What does that mean to say we map a 3-dimension into 2-dimension? Okay, and this is a simple geometrical meaning of that. So there is a matrix here. If you pre-multiply this point, that will fall onto this point. But the interesting thing is, this is a 3-dimensional point. It cannot be put on a 2-dimensional space or 2-dimensional plane. But here it is a 2-dimensional point. It doesn't exist in 3-dimensional space. I mean, it does exist with zero. Y is equal to 0. Okay, but there is no. This is x, this is y, and this is z. Okay, z-axis. So with that introduction, I introduce you to what is called the eigenvalues and eigenvectors. Okay, how did I go from here to here? Eigenvalues to eigenvectors. I was asking the question. That if I am doing this, there must be a different set of access properties, and these are different set of access properties which are either expanded. Lambda refers to some kind of a weight to that each of the axes, right? So either it expands an axis more than one or less than one. Okay, but the point is, if I can find a solution, solutions to a system of equation Ax equal to lambda x. Think about it. Again, I'm going back to the solutions of equations. Okay, if I can find the solution for systems of equation Ax equal to lambda x, think very carefully. What does that mean? It means the constant weight we want to find out, and also we want to find out these x vectors, isn't it? There are just more than the x vector values. When we solve for problems, where Ax equal to b, we solve for b, we solve for x, but we are also giving ourselves the opportunity to find out whether are there weights that change the axis in the new axis, gives more weight to certain axes, less weight to certain axes, and so on. Are you with me so far?
Yes.
Cool. Very nice. Because this is difficult to understand actually. இது எங்க இருந்து வருதுன்னா, இது புதுசா இருக்குது, எங்க இருந்து lambda புதுசா போறோம், ஏதோ some parameter value, we don't know, so we call it as lambda. That's a standard, mathematical symbol. So the point is really, we are trying to find out, what is this transformation A. Okay, what is the transformation A? Which will transform the original data points into a new access systems, and that the question is answered by this equation. Again, we are trying to find out a transformation matrix that will take the original data points into a different set of axes. But the benefit of different set of axes is that I can identify which axis has more, more observation space and which axis has less observation space. Are you with me?
Yes, sir.
Okay. So that is what is really giving the eigenvalues and eigenvectors. It has a lot of different interpretations, but we want to only concentrate on the big data interpretations. So we have a systems of equations in lambdas and unknown, and that gives us the eigenvectors and eigenvalues, and from there I jump literally I jump to what is called the PCA. Okay, so for PCA, principal component analysis, we can also call it as principal axis analysis, because I have been only talking about, in fact I like the word principal axis analysis because it's defining a new main axis. Are you with me?
Yes, sir.
Okay. So, why am I interested in that? Because there are two important matrices in big data. One is called the variance covariance matrix, and here is the definition of three variable variance covariance matrix. The other one is correlation matrix coming out of this. Okay, the difference between this variance covariance matrix and correlation matrix is now you divide each of these rows and each of the column by their corresponding standard deviation. That's the only difference. But why do I need that? Because in some problems, we will be working with the correlation matrix, not variance covariance matrix. But in the case of PCA, we will be using variance covariance matrix. Now, what is the problem in variance covariance matrix? The variance covariance matrix is telling us, let's say this is 1000 variable variance covariance matrix, right? It is telling us that the data is spread in 1000 dimensions. But in reality, most of the problems are not that much uncertainty in the data. Okay, most of the problems. I don't even know any one problem that tells me, there's a 1000 dimension data space which you have to use where you have to use all the dimensions. Okay, so most of the problems are lower dimension data, lower dimension intelligence. In fact, it's amazing. Recently I read an article about determining the age of the universe. You might think that it is a mind-boggling question, right? But it's a very simple linear regression, So it's amazing. And actually they use simple linear regression to estimate the age of the universe. So most of the problems are very simple. And so, we have to figure out a way to find those simplicity in the data. Okay. So variance covariance, in this case, what we are saying is, the data is spread in 3 dimensions. Do I really need 3 dimensions? That's the question we are asking in PCA. Okay, and okay. So then, how do I find those? The principal axis. So we know already the principal axis are definable using the eigenvectors and eigenvalues. Everybody with me?
Yes, sir.
Okay. So, we talked about that, more about eigenvalues, eigenvectors. I kind of solved these problems for you. Do you remember all these things? Do you remember all this, having solved these problems?
Yes, sir.
Okay. Yeah. Thank you. All right. So I have these examples, very interesting example, an example of a single vector as a generator. Sometimes the eigenvectors are also called generators because that generates the data, right? You can go back to the data, origin data, using those eigenvectors, either approximately or accurate, exactly. Why I say the word approximately because if you use less number of eigenvectors, you will get approximate. Okay, and so here some notes are there, and I want to come to this one. Okay, and I did attend to this one also. But by the way, we have a lot of things, but one of the things a lot of things we are going to cover, okay, today. Like I'm going to introduce, what is called factor analysis. I'm going to introduce uh, correspondence analysis. I will introduce singular value decomposition. Okay, all these things today I want to achieve, and if possible more. But then at least if I can achieve that, that's great. But I always do this. When I go to a class, there is always a gap between the previous class and the current class. So I like to review, and that's what I'm doing. So don't worry about the time. Okay, it's all good. In fact, in my class, I ask everybody to tell me in your own words what is PCA. Does somebody want to try? You don't even have to look at this one. It should be in your in your heart and mind right now. What is PCA? Say that in a few words, because this is going to be a interview question.
PCA is principal component analysis, where we try to reduce the dimensions by finding the most important significant variables we have in the data sets.
Significant access.
Based on the significant access, we find out the significant variables when needed.
No, significant access. I never said, I don't think I ever said, significant variables, significant access, which is a significant, you can call that as a significant variable, but I call it a significant access. I insist on significant access only to get more clarity. Okay, it is a significant variable in the new transform space.
But we reduce the dimensions, right? The dimensions in the sense they refer to the variables. Like if there are more than 200 variables, maybe we reduce it to 80 or 100 variables.
Yeah. Variables means okay. Let's understand that definition. Okay. So here is actually the formula. Here is actually the formula, right? That is where sigma is the variance covariance matrix, and it is decomposed. This is called a decomposition. Decomposed into, because it says P by P matrix, maximum it can have is P eigenvectors with the corresponding weights for each of the eigen direction or axis direction. Okay. So if I in the new transformed space, because it's in this case it is it's not a transformed space, but it's basically a rotation. In this case, it so happens, very particular case we are talking about. It's really shifting the location and translating the the rotating the axis. Are you okay?
Yes, sir.
Okay. So we are shifting the location and rotating the axis. That's what we are doing. But in the process, the old points are defined with using new axis. The old points are redefined with the new axis. That's why I'm calling it as the principal axis. So what we are looking for is the most relevant principal axis that explains the old points with the least loss of information. Okay, or with the acceptable loss of information.
Okay.
Okay. Satya, correctungla?
Okay, sir.
Prashant?
Yes, sir.
So what we are saying is that see, the understanding all this is very fundamental. It will make you a free person in terms of how to think on data science. So that's why I spend much time here, even though it looks ugly, right? The formula looks ugly. Look at this. Okay, but once you get used to it, will be okay. But the point is, in the new rotated representation, that's a good word. In the new rotated representation, the new axes are not the original variables. The new variables are if you call it as new axes, new variables are this one. the new eigenvectors directions. If you want to call new variables, maybe you can say, each of the eigenvector is a new variable, because there we say, not eigenvector, but each of the members of the eigenvectors are the new variables. Are you with me?
Yes, sir.
Because, in the original vector, in the original data also, we have the original data x1, x2, xp, right? And those are the original variables, x1, x2, xp. Now we are reducing it to, let's say, 3 or 4 or 2, something like that, right? So, but in this case, these are the eigenvectors define the new directions and the new axis, and leaving out the remaining directions and remaining axis. So if you want to keep variables, that's fine, but I think it is much more. It's more clearer if you say you are in the new directions. You are using the new directional variables. Maybe it is better to add the variable for clarity. That's fine. Okay, but I like the word principal axis, principal vectors, principal dimensions, principal directions. Okay. Now, I want to introduce another concept. This is also called, I think I mentioned that, this one. I mentioned that this is also called spectral decomposition. Did you hear that word? Spectral decomposition. There are different names. So that's okay. It's also called principal. This is also called eigenvalue decomposition or spectral decomposition. Now, take a look at this one. What is the difference between this and this? Can somebody tell me? Very easy difference. What is the difference between this matrix and this matrix? Can somebody tell me?
First one is a square matrix because number of rows and columns are same.
Excellent. Yes. That is the difference. Big difference. Okay. So the question is really, for a square matrix, you have this kind of decomposition. The question is, for a non-square matrix, do we have a decomposition like this, similar to this? Okay. Now, mathematicians have found that yes, we can do that. So now your immediate question is, where do I apply this? Right? Can we apply this or not? Why are you talking about it in our class? It's a big data science, right? Why do we care about this one? If you later on, I will teach what is called the recommendation engine. Okay, that recommendation engine is a non-square matrix, non-square, non-symmetric matrix. Okay, so there is M is the number of people, N is the number of ratings of movies. So it could be 100,000 people and 20 million people and 100,000 movies ranked in Netflix.
A non-square matrix is we can decompose, right?
Yes, that's what I'm saying here.
Yeah, but for recommendation engine, you said we cannot.
Yeah, go ahead.
Actually, I just got confused, sir. When we're talking about spectral decomposition, for square matrix it is possible, and non-square matrix, as per statisticians, it is possible.
Yes. I'm trying to tell. Yeah, sorry.
Okay. Continue, sir.
Be loud, please.
Yes, sir, I got it.
Okay, cool. Very powerful result. Very powerful result. They both are powerful. I'm not saying that this is anything less, okay? But the point I'm saying, I'm just want to give you a directional thinking. Why do I care about this? For example, like that. Okay, I'm going there to say that, hey, you know what? For a recommendation engine, for example, movie rating, this is, let's say 1,000 people, this is, 500 movies, then, it's a non-square, non-symmetric. But can we decompose that into a structure like this? And you can see that it is the same structure. Do you see this? Right? Same structure, but I use a different symbol, that's all. And the only thing is that, there are some differences. Here it is U1, here it is both are same, isn't it? But here they are not. U1 multiplied by V1 transpose. And similar to lambda 1 eigenvalue, here what we call as singular value. Okay, these are called singular values. So singular value delta 1 U1 star V1 transpose. So if you want to take only the first dimension of this reduced matrix, reduced representation of this matrix, then you will just stop with this. But if you want 2 dimensions, you will stop with these 2. So there are 2 singular values instead of, the names given here are singular values. And the vectors are called singular vectors. And you can see that it keeps on going, but what is the end here, That is the minimum of M and N, because it cannot have access beyond the minimum of M or N. Okay? Minimum of M and N will be the end point here. That is what actually it kind of went down. It should have been plus here, Let me see whether I can move it there. What I'm saying is, it should be, yeah, there you go. So by, hopefully by putting it like this, you realize this, it's in good place. Are you with me?
Yes, sir.
Okay. So now, how do we do this? How do I calculate similar to, the variance covariance matrix? Can I calculate this? Is there a package available? No, of course, yes. R we have, every language has it. No worries at all, whether it is R, Python, or SAS or whatever. Okay. So I will go over that later. So, well, let me see. Now that I have come so far, let me finish this also. Here is the another slide that I want to share with you. I do get excited when I share these kinds of very powerful tools. SVD, it's called singular value decomposition. The most powerful mathematical tool for dimension reduction. Why do I say that? Because this also subsumes the spectral decomposition, because that is a special case of this. Okay, and so I'm going to let me walk you through this example, how to get singular values and so on. Okay, ready? Let's use it as this with R. Why it is okay. I have to do something about this. It's not coming through well. Usually when I click on it, it comes through well, but not this time. Why? Can you see better now?
Yes, sir.
Yes, sir.
Okay, good. Thank you. So I'm going to run this example and explain to you what happens, how it happens. Again, the ideas are simple, simple. The idea is to reduce the dimensions. Okay, so let's define a small matrix M1. Okay, and before that, I want to take some options in R. I'm going to open R. Okay. By the way, I sent a message in PA1 for you to do some assignments. Did you all get it?
Yes, sir, we got it.
Okay. Please do them because they are very simple, but it gets your focus. Okay. All right. I'm just going to copy and paste here. So M1 is defined as this matrix. Are you with me?
Yes, sir.
Okay. Let's keep doing. And then I'm sorry. There's a very simple command called SVD. So I want to do the SVD, singular value decomposition of M1 matrix. It did it, and what does S1 contain? It contains, it shouldn't be surprised that it contains singular values which are called D. Okay. Singular values, and then the U matrix and the V matrix. Okay, U matrix and V matrix. So far so good. And
Yes, sir.
from this, I should be able to get back my original data, isn't it? That's what it says. Decomposition means all these things in a certain way I combine, I should be able to get back my original data. Agreed?
Okay.
Okay. So first I want to define what happens if I use only one dimension. What happens instead of using 3 dimensions? What happens if you use only one dimension?
Sir, we are unable to hear you properly.
Oh, can you hear me now? Hello?
Now it's clear, sir.
Okay. So,
Hello.
what I'm saying is, I have created a toy matrix M1. And then I did singular value decomposition of that matrix. Okay. And I got these are called, remember, singular values. We don't call them as eigenvalues. Okay. And this is U matrix. And this is V matrix. In the case of spectral decomposition, we don't need 2 matrices because you just need eigenvectors, eigenvectors matrix, and just it is only one. Okay. Now, sorry. So I was saying that I should be able to, if the promise is correct, that singular value decomposition creates a decomposition of a matrix of a non-square and similar matrix, which is what this is, right? This is non-square, 4 by 3. All right. Then I should be able to get back as I keep increasing the singular dimensions. As I increase, I should be able to get back my original data. Okay, I'll try with the first dimension. Okay, so I got the data. S1 contains all the objects. Out of that, the U is the left multiplying matrix, and V is the right multiplying matrix. Are you with me? U is the left multiplying matrix, V is the right multiplying matrix. So I can pull out the specific vectors for each of the singular dimension. So U1 is the first left eigen. You can call it as left singular value, singular vector. Okay, left singular vector. U1 is first left singular vector associated with the first largest singular value, and the largest first singular value is taken from the D vector. I convert that into a diagonal matrix, and then even though I take only one parameter, only one point, right, only one element, I still need to consider, convert them as matrices. That's why I do all these things. Are you with me, guys? Okay, so what I am saying is, you understood up to this. Are you with me?
Yes, sir.
Okay.
In S1, we are having all the objects.
All the objects. And there are, what are the objects? Only three objects. One is the singular vector object that is given by $D, and the left singular matrix object, and then right singular matrix object. You see? Where did I wanted to show it to you. No. What happened? Okay. let me I will come back to that. I thought I shared with you earlier. Okay, I'll go back to that. And then we can see this one. You see this one? This is left singular matrix. This is coming from the right singular matrix, but only one vector at a time we are talking about. Are you with me? This is a left singular vector from the left singular matrix. This is the right singular vector from the right singular matrix. Is it okay so far?
The U and V are singular vectors only, right, sir? The delta is singular value and U and V are singular vectors.
Can you repeat that question, please? Once again, I'm not able to, I need a little bit more sound.
Delta is singular value and U and V are singular vectors, right?
The SVD decomposition returns singular values and the left and right singular vectors as a matrix. So there is no one eigenvector dimension, right? It's now on. It is managing on the left side, on the right side, both sides. So it creates two different collection of singular vectors. One is the left side and the other one is right side. Are you with me?
Is that a vector or a matrix? The U and V?
Sorry, our words are mixed up.
U and V are vectors or matrices?
Oh, U and V are matrices. U1 is the first singular vector from the U matrix.
Okay.
It is like this is a E matrix. Out of this, epsilon 1 is the first eigenvector. But because it's symmetric, you don't have a problem on the second, the right side. But here it's not symmetric. So we have to find both the condensation on the left side, condensation on the right side.
Okay, sir.
Good. Okay, so let's go back to that. So I was saying here, when I do SVD for any matrix, this could be recommendation matrix, right? So, the R provides me three objects, that is singular values vector. This is really a vector. It's not a matrix, right? But I convert into a matrix because I need to do matrix multiplication. This is, I'm pulling out from U matrix. You see this one, U is a matrix, B is a matrix, U is a left matrix, and I'm pulling out only the first column. Are you with me?
Yes.
Very good. Because once you understand this, the rest of the explanation will go very easily. Again, I do the same thing. here I'm pulling out only one element, but I do a little bit of tricky representation here so that I have to diagonalize it even for one element and then make it as matrix. Then only I can do the matrix multiplication. Correct? Enapa Satya? Okay. So, ரொம்ப இம்பார்ட்டன்ட் இது வந்து வெரி பவர்ஃபுல், வெரி இம்பார்ட்டன்ட். அண்ட் இது இல்லாம நீங்க வந்து ரெக்கமெண்டேஷன் இன்ஜின் பண்ண முடியாதான்னு கேட்கலாம். Okay, yes, you can do it like anybody else, but that is not how we want to train you. We want you to get to the foundations, okay, so that you can independently think certain things. Okay, in fact, it is so advanced, sometimes people don't go there at all. They'll simply do some foundations, very basic, row calculation, column calculations. Okay, anyway, I am saying up to this is fine. Are you with me, Satya? Correctங்களா? Yes?
Yes, sir. Yes.
Okay. So in English, what are we doing here? I am pulling out the first column vector of u. I am pulling out the first column vector of v. Okay. First column vector, okay, of v, and then first singular value of the singular vector. That's all I'm doing. So if I do any mathematics here, combination here, it's all about only first singular dimension. So far so good. That's all in English. I'm working only with the first singular dimension. Are you with me?
Yes, sir.
So என்ன பண்றதுக்கு ட்ரை பண்ணிட்டு இருக்கேன், ஒரு சிங்குலர் டைமென்ஷனை வச்சு காமிக்க போறேன். நான் மேட்ரிக்ஸ் வந்து பாருங்க, I'm retrieving only using first singular dimension a matrix M2. I'm retrieving a matrix M2. But if that matrix M2 is, I expect that it is closer to M1. Are you with me? I see. I'm retrieving a matrix by matrix multiplication of the singular value, left singular vector, and right singular vector, and they're all converted into matrix. Okay, because this is a matrix calculation. Really, in the end, this is a matrix. Do you agree with me, everybody? Yes or no?
Yes.
It's a matrix. Everybody?
Yes, sir.
If I combine these two, again it's a matrix. Everybody?
Yes, sir.
Okay, good. So what am I trying to do? I'm trying to show it to you that by taking only smaller slice of the dimensions, I'm trying to approach closer and closer. And you will see when I include all the dimensions, in this case only 3 dimensions, because the minimum of the matrix size M1 is 3. Okay. So I retrieved a new matrix called M2, which is a calculated value from the first singular dimension only. And I compare it with the M1. That's what I'm going to do. And you'll see that will be closer, but it is not as close as I include 2 dimensions. That's what is happening here. Are you with me? But I'm not calculate பண்ணி காமிக்கல. I'm just telling you that's what I'm going to do. Where I am driving you. But for that I need U2. Now it's a matrix using 2 columns of U matrix. 2 columns of U matrix. And I need 2 singular values from the D vector. Are you with me? And then 2 columns of V matrix. Is everybody with me? Why do I do that? By moving from 1 vector to 2 vector, I will try to show you that the M2, now the latest M2 is more closer than the previous one. உடனே நீங்க கேட்கலாம், சார் இது எதுக்கு சார் நீங்க எல்லாத்தையும் 3 வெக்டருமே போட்டு காமிச்சிருங்களா சார், அது ரொம்ப சிம்பிள் ஆச்சு அப்படின்னு தோணும் இல்லையா? So that's what I'm doing in the next iteration. I take all the 3 vectors, left singular vectors, define it as U3. All the 3 singular values, I define it as D3. I take all right singular vectors, 3 singular vectors, only 3. Remember that, it won't be more than that. It doesn't matter whether left or right. I call it as weak 3. Then, do you agree with me that this one, look at this one. What is this? As matrix M1 minus M2. What is M2? M2 is retrieved using 3 singular dimensions. Agreed? That's what M2 is. And the difference will be the least. Pretty much it should be same, not least. We will see that. Are you ready? Do you understand what? Sorry, so can you repeat?
First ஒரு காலம் மட்டும் வச்சு எடுத்து பார்த்துட்டு இருந்தோம். இப்போ நம்ம அடுத்தடுத்த காலம் போனது
அடுத்தடுத்து I'm adding, yes. I'm adding more, yes. Shall I run it? Maybe if I run this chunk by chunk, you will be able to see what I'm saying.
Okay, sir.
I'm sorry?
We will run it and see what.
Yes, that is correct. Okay.
Different statement, why are we subtracting, sir?
Yeah, so why am I doing this? Good question. Why am I doing this? That is my ultimate aim, to show you at every stage that I am more and more becoming closer to the original data. That's my problem. More and more closer. What is the original data here in this one? M1. What is the retrieved matrix?
M2.
M2, exactly. So I want to see the difference. Is it a good purpose? Okay, let's run it. I think, I gave you a whole idea here, but let's run it and, get convinced, get, assuaged, Are you okay now? I'm going to do this.
Okay, sir, I understand. Finding the difference, we're going to see how the retrieved matrix is equal to the original matrix.
Exactly, yes, absolutely. Thank you. I like when you speak in English terms, because English term means any language is okay, but simply pesnaka onnum puriyadhu, adu useless. So just now what you said, it makes me happy. Okay, so but what did I do here? Look at this. I used how many singular directions I used for retrieving this matrix? One. Okay. I used 1 and then I found the difference here. This is the difference. Okay, but ingella 0.91, so I don't know what's going on. Let's go with the next one. Next 2 more. Not 2 more. 2 dimensions. So now I'm going to use U2 using 2 singular values. Okay. So what would you expect this to go?
The difference should decrease.
Decrease. Yes. Let's try. Ready? Here you go. Okay. Do you remember the previous difference? Now this, you can see almost all of them have first digit is 0. But if you go back here, none of them is first digit is equal to 0. Are you with me?
Yes, sir.
So how about we go to the third possibility? It should be absolutely same, right? Except for rounding error. Agreed?
Yes, sir.
Let's try. Do you see this one? What is this? Print the difference, M1 minus M2. This is just a rounding error. So we got same matrix M1. So I just try to show you, impress you that this works. It works perfectly. That's all my purpose was. 1 second. Any questions?
Going for SVD,
மூணு ஐகன் வெக்டர் மூணு வெக்டர் அந்த ஒண்ணு மட்டும் யூஸ் பண்ணி நம்ம மேட்ரிக்ஸ் ஒரிஜினல் மேட்ரிக்ஸ் அதான் நிறைய ஒரிஜினல் மேட்ரிக்ஸ் அதே மாதிரி ரெண்டு வெக்டர் யூஸ் பண்ணி டிஃபரன்ஸ் பார்த்தாலும் கொஞ்சம் டிஃபரன்ஸ் வரும். மற்ற எல்லா வெக்டர்ஸையும் போட்டு பார்க்க போகும்போது டிஃபரன்ஸ் ரொம்ப வரும். எல்லா வெக்டர்ஸையும் அதுதான் ஒரு ஸ்கேலர் வேல்யூ வச்சுட்டு
So I have given you a very powerful pathway, not just for square matrix, but even if it is non-square matrix, you can do the decomposition and reduce the dimension. That's the purpose, right? By only using limiter. I don't know why I'm
Sir, your voice is breaking.
Yeah. How about now? Can you hear me better?
Yes, sir.
Okay, I kind of muted the on the other side, but then I will not be able to hear if people at IOA ask questions. That's a problem. Okay, I'm going to unmute and then ask questions here and there. Okay, because otherwise the quality of the audio is not coming well. Okay, all right. Now, so the whole idea of big data reduction is all about utilizing principal access or principal singular access. Principal access or principal singular access. Okay, it's all about it. Even if you have 10,000 dimension, doesn't matter. It's a relatively beautifully is doable using our matrix decomposition method. While the eigenvalue decomposition or spectral decomposition is useful for reducing the dimensions in terms of the original data. In the case of singular value decomposition, it is reducing the dimensions for non-square matrix. Okay, that's all to it. Okay. Now, I want to introduce a new concept called factor analysis. Did I introduce this to you or not before? No, right? Okay. Let me introduce you a concept called factor analysis. Again, why do I talk about it? This is dimension reduction again. Okay. In factor analysis, we again reduce the dimension. So what is the difference? We already reduced the dimensions in principal component analysis, principal access analysis. So what is the fun here? What's the purpose here, right? The problem is oftentimes data are measured with error. Okay, so it is very common in psychology. Measurement with error is very common in psychology, psychometrics. Okay, but the thing is, these are all applicable in talent management also in big data world. Does that make sense? In talent management, it's very difficult to measure the true intelligence of various dimensions in an individual. Do you buy that? Oh, maybe.
Talking about the difference between PC and factor.
Yes.
I couldn't correlate what you said.
You didn't hear well?
Yeah, yes, sir.
Okay.
Explain it again.
Okay, so what I'm saying is, after I explain one more time, I will unmute IOA. Okay, so what I'm saying is, now before even going to this example, so let's take this example. Okay. This is a student grade in finance, marketing, and policy. Okay. And this doesn't have to be only 3 variables. it could be 10 variables and there could be hundreds of students, right? Or 15, 20, 30 variables. But how do we make decisions with 20, 30 variables about who to select? Yeah, got it. Thank you. I don't know what to do. There is some background noise, but where it's coming from, I don't know. 1 second. I'll try to test it now. How about that? Hello? See, when I muted Prashant also, there is no noise. Do you agree with me, IOA? When I muted Prashant also, there is zero noise. Do you agree with me? Prashant, do you agree with me? Oh, okay. You opened up and then it's again giving noise. So you can type also, okay? All right. Now, I will unmute after I explain this. So the point is, how do we, we cannot make decisions with 20 dimensions about, somebody's talent. We just need 2 or 3. Ordinary people cannot interpret beyond 3 dimensions. Even 3, they will fall off. That's why most of the consulting business, they will always use a 2-dimensional chart. Do you know what I'm talking? In most of the consulting, they'll use only 2-dimensional chart. So the point here is that finance, marketing, policy, all meant to capture probably only 1 or 2 dimensions. Can you guess what it could be? Somebody? For me, it looks like finance and marketing is more about numerics. Agreed or not? I had to open up. You can type. Can you please type? Let's try that method, IOA. Okay, Prashant. Okay, cool. Very cool. That's wonderful. Let's try to use this method also, because here the noise is less. Okay. So I'm saying that not necessarily that I know this. In fact, I don't even remember what the results are. Okay. I'm just saying finance and marketing is more related to numerics, and finance and policy probably are related. Some part of finance and policy are related to some what is called touchy-feely dimension. Okay? Does that make any sense to you? Type, please. Okay. So I'm thinking probably, so what I'm saying is internally we care for numeracy. Internally we care for their ability to make decisions. Okay. And of course, what type of decision depends on what type of variables we measure. I agree. But the point is, it's not really about, the scores here in marketing, finance, and policy, but it's probably more about based on the data. I'm not saying that. I'm just saying probably the data, probably the data points out to that kind of hidden intelligence. Do you buy that? Hidden intelligence. Okay, probably the data points to such hidden intelligence. The keyword is hidden. Yeah. Y1, Y3, Y1, Y2, or Y1, Y2, Y3 all combined, whatever. Okay. So the point what I'm trying to bring up to you is that it's not just a linear combination of these variables which defines a new transformed axis, also rotation of axis, that defines PCA, but it is the inside, internal, hidden dimensions we are talking about. Do you buy that? Hidden dimensions. I'm not talking about the rotated, original data, rotated, translated dimensions. Do you see the difference? Oh, well, we'll come to that. We'll come to that. But do you see the point I'm making? On what basis do we identify that? We are going to do that. We are going to do that. Okay. Prashant, are you with me? In fact, it's a mind-blowing ideas. These ideas are unbelievable. How these people think. I'm going to show it to you, bring it out to you using mathematics. Enna Prashant, puriyunala? Please type. I'm not able to see. Oh, I'm not able to receive anything from you, Prashant. Oh, yes, sir. Okay, good. Thanks. So, I'm trying to listen very carefully. This is a number Jitan Valanonga. Okay, they'll say this is this is like a magic actually. That we say that the data has errors. Point one. Okay, we are trying to capture some actual intelligence about numeracy, ability to make decisions, this and that, which are very difficult to capture. So we capture like this, right? We capture like this. So how are we going to get back to those hidden dimensions? Can we? So statisticians said, yes, we can. As long as I can find out the hidden dimensions from a structure, which I'm going to call it mathematically. Wait a minute. One moment. I have to say the word sequence correctly for you to appreciate this. Okay. So, as long as there are linear relationships among the hidden dimensions, I will be able to pull it out. I'm not talking about linear relationships among the original variables. I'm talking about linear relationships among the hidden dimensions. So the idea is that if fundamentally there are only two dimensions, F1, F2, let's call that loosely as quantitative ability, and F2 is verbal ability. And the score Y1 is a function of F1 and F2. Y2 should all, because we are saying only there are two dimensions that defines all these three scores. So I should be able to rewrite Y1 as a linear function of F1, F2, Y2 as a linear function of F1, F2, Y3 as a linear function of F1, F2, but with some error, because we know there is an error here. We said this is supposed to capture some hidden dimension, which we try to. Okay, we try to implicate such dimensions, but we may not be successful. So that's why we need to be, validating our testing procedures, interview methods and all those things in talent management. But nonetheless, do you understand, do you buy this statement that original variables are Y1, Y2, Y3, but now I'm rewriting it into only using two variables? I don't want to call it as variables, but I'm going to say it nonetheless because Aruna, you said, remember variables. It's actually two dimensions here, right? Because I can cut down one of the dimensions also if there are hundreds of dimensions. Everybody buys that first line? If you understand this, it's the factor analysis is done. It's a difficult concept, but if you understand what I explain, it's done. I know it's just a matter of computations only, but anyway. So then the question is really to estimate beta 1 0, beta 1 1, beta 1 2, beta 2 0, beta 2 1, beta. These are the unknowns. Sorry, F1 F2 is also unknown than I am. Yes, of course you are right. It's also unknown, right? There are actually, very interestingly, not only beta 1 0, beta 1 1, beta 1 2, but also F1 and F2 are unknowns. Do you buy that?
Yes, sir.
Good. Very good. Very good. So what did I establish here? I said the whole collection of variables, it could be 10, 20 variables, are written only with two hidden dimensions. அது என்ன சார் நீங்க ரெண்டு மென்ஷன் பண்றீங்களே, how do you know that that is enough? Is that a fair question?
Yes, sir.
It's a fair question. என்ன கரெக்ட்டுங்களா அருணா?
Sir, number 20 variables, we are going to split it into two variables, that is F1 and F2.
Yes. It's possible, that's all I'm saying.
It can also be, okay. It is also possible to put in one variable also.
Yes,
Right?
yes. But we have to let the data tell us how many dimensions we need. And that's where we use the decomposition formula again. Get it?
Okay.
But this time we are using the decomposition formula in the hidden dimensions. புரியுதா? And that will happen, no worries.
Hidden dimensions. Okay, sir.
Yeah, the F1, F2 are hidden. They are not openly known to you, known to us. See, in PCA, we are rewriting your principal vector values, new principal vector values using your original dimensions. Here, it's not like that. Okay. All right. Now, and these are called beta values are called loadings. I know I just want to open up a little bit IOA people so that they can speak to me. I'm sorry about that. Kind of. IOA, can you speak with me? You are muted. Why? Self-muted. Okay. I can't help you. Okay. How are you, Satya and Aruna?
So it was a little bit fast, so we weren't able to follow. That's why I messaged.
Yeah, அது correct. புரிஞ்சுது எனக்கு. I saw your message, but are you able to? Could you please? Oh, I see. I didn't see that. Could you please repeat once again? So, which part? What I'm saying is,
Like when you were saying that y1 is a function of linear combination of f1, f2, and even if there are more variables, you were saying something that part. From that, we were not able to follow correctly. The words were not able to capture.
Okay. Right now I will. Okay, fine. So what I said is there are 3 scores only we are measuring here, right? In this example, that is finance, marketing, policy. And what we are saying is 3 scores. Maybe only fundamentally they may have F1, F2 as 2 dimensions, explaining these 3 scores with these parameters. We don't need more than that, possibly. Now, this is a over parameterized. You understand that because there are only 3 scores, but then I have 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters, and then the dimension F1, F2 itself is another what is called the independent varying information. So there are too many to over parameterize here to explain this one. This is just a toy representation to understand. What all I'm saying is, no, let's say in real life, you may be 20 scores, 20 different scores you will have. You are taking classes in MBA, and there are each of the courses you get scores, 20, maybe 10, I don't know how many courses, 12 courses you will have on an average. So you have 12 scores you have. And the question is, it may be, the talent management office is interested only in the first 3 dimensions. Are you with me?
Yes, sir.
Okay, that's all I'm saying. And those dimensions are different from PCA. The PCA is just a translation rotation of the original data. But here we are talking about not only translation rotation, issues are coming in by its nature of data by nature, it will come. But the point is, it is in the hidden dimension. So in the hidden dimensions is where we pick up this axis, F1, F2. So what all we are saying is that the original scores are measured with the error, epsilon 1, epsilon 2, epsilon 3, having linear relationship with the hidden dimension. These are called latent dimension. Latent, that's why it's called factor analysis, is also called latent variable analysis. So far, so good?
Yes, sir.
And in real life, it may be 20 different scores, as I said, and you need only 2 or 3. Okay, that's a reality. So there are some assumptions here. The error terms are independent. We need those things, okay, because Otherwise, it will be very. There are methods. People have devised when there are dependency and so on, but it will break down. So what you have to do is, you design the testing procedure. You design the data collection procedure in such a way that this becomes valid, so that it becomes easier to accomplish the results. Okay. The other thing is the unobservable factors, F1, F2, in this case, are independent of one another. They cannot have correlations again. Okay, independent of one another. And these are all just terminologies. So just to buy into it, don't worry about it. Okay, the betas are called loadings or loading, factor loadings. Yeah, they are called factor loadings. Okay, because they weigh.
Sir, Arun has asked a question.
I'm sorry. What is that?
Aruna has asked a question.
Oh, okay. Well, only 2 latent. No. I mean, in this example, 20 variables. I said 20 variable. 12. Let's say this is all scores from MBA students. Okay, there are 12 courses usually, around 12 or 15. I don't know, some number. So you are talking about this, all the 15 scores rewritten as probably 2 or 3 dimensions, or maybe 4 dimensions. I don't know. So we are not talking about all problems are solved with 2 latent dimensions. I'm saying reduced latent dimensions. Are you with me now? Okay, cool. Thanks. Get my attention like this, Prashant. Thanks. In case I miss.
Yes, sir.
So, there are some assumptions, okay, but there are some terminologies. Any science is a collection of new terminologies. Beta 1, beta 2, beta. These beta values are called loadings, okay, factor loadings, because they are, I don't know. I would like to say weights, factor weights. Why do we unnecessarily introduce new word, right? I'm a kind of like that. I'm a kind of person who wants to achieve maximum with a minimum words. Maximum information with minimum words. But anyway, historically people have used the word loadings, which is basically the weights for these factors. All right. Out of that, so what is happening here is that for each of the yi observation, if you calculate the variance, then it is basically, it's a constant, you square it, and in fact, if it's a constant, the variance, it zeroes out. Okay, there's no variance for a constant. So if a variance of yi is beta I1 square, variance of f1 plus beta I2 square, variance of f2. That is the formula for variance. Constant times, if you have variance of ax, variance of ax is a square times variance of x. Okay, that's a formula. So each of the variable is variance is written like this, and out of that, this is called communality. The first part, the beta, the loadings related, is called, again, it's just a historical terminology, communality, and this is a specific variance to the particular variable. This is specific variance, and this is called communality. Sorry. Just a terminology. Okay. Thank you. Just some terminology, remember. Okay.
Yeah.
So no worries about it. Don't get bogged down here or worried about I used to be, when I was a student, I was going crazy. I don't know the communality. Every word you have to have a நம்ம ஊர்ல சொல்லுவாங்க, தமிழ்ல சொல்லுவாங்க, காரண பேரா இருக்கும். எனக்கு அப்படி இருந்தாதான் புரியும். ஏன்னா அது easy to retain, explain, communicate. Communality, I'll find out. Okay, but this is specific variance. That makes sense. I would say common. It's a common variance for y1 in this. For yi, this is yi. For y1, this is well, everything is yi. Okay, so y1, y2, y3. Just change the I values. Okay. Now, so we use this structure to find the answer. Okay, I'll come to that. A little bit more work, hang in there. How are we doing? Are we okay? I'm not losing you guys, right? கொஞ்சம் கஷ்டம் பட்
No, sir.
கொஞ்சம் அது படிச்சிட்டோம்னா சார் you will be proud. I'm when I learned this, you won't believe, after years and years after I understood this. My teacher didn't explain. I'm not complaining here, but what I'm saying is it always bothers that something எதுக்காக ரன் பண்றாங்க தொந்தரவு பிடிச்ச வேலையா இருக்கு. நான் சொல்ற ஒரு சீக்வன்ஸ் ஆஃப் வேர்ட்ஸோட உங்களுக்கு கம்யூனிகேட் பண்ண பார்த்தீங்களா, அது that is I learned it only after a long time. Okay, so I'm very happy to share that with you. So anyway, the if I do the variance covariance matrix for yi, then I get this. Everybody understands this part? Because the covariance of y1, yi, yj is this one. Okay, you can do this. It's I want you to do this as a homework, but it's doable. Given this expression, I gave you this expression, right? Right? Given that expression, you can check it out. It will be covariance will be like this, variances are like this. The specific variance is only coming in the diagonal, isn't it? Now, let's rewrite this in this form. Okay, are you with me? I rewrote it in this form. Yes, excellent. Okay, so S1 square is the observed variance. Wait, one minute. Okay, this is observed data. This is data related variance. Okay, this is theoretically I was trying to explain all these things. Okay, but now with actual data, this is what I get. Now, this variance covariance matrix, I can make it into a correlation matrix. Are you with me? What do I have to do? I just have to divide 9.84 divided by, this one is 9.84. So if I want to get a correlation matrix, this will be 1, this will be 1, this will be 1, right? So correlation between 1 and 2, variable y1 and y2 is minus 0.036 divided by square root of 9.84 times square root of 5.04. Everybody agrees?
Yes, sir.
Okay, cool. So what I'm saying is, given the original data, I can calculate variance covariance for the original data or the correlation matrix. Okay. Now, how am I going to solve the problem of finding the factor weights? Right. That's all I need to do.
Here we saw observed variance, right?
Yes. Yes.
What is that, sir? Can you explain?
Observed variance. It's coming from the y data.
Y data. Okay.
Yeah. Y is
that is
y1,
original
y2,
data,
y3.
right?
Yes, that's the data, right? Data points. From there, I get that. Now, I want to just get your attention how I get the factor loadings. It's a toy example, but it's okay, And then we will, as usual, we will quickly jump into matrix representation and then satisfy ourselves that it's all working good together. The problem with the loadings is that it may not be unique, and in fact it won't be unique, and that's okay. There are ways to make it unique and so on. But let's just find out some value that we assign like this. What are we saying? You go for the first guy. For the first code, you have whatever the F1 is, weigh 50%, 50%, and to get you can get the data. For the second one, 30%, 30%. Third one is 50% F1 minus 50%, weighted differently, So weighted down. F2 dimension is weighted down. So in this case, if I have these kinds of weights, then we can just calculate this and it turns out to be like this. Okay. So we can calculate that. No, don't worry about it. It's doable, very straightforward. When I say very straightforward, do you buy that? At least emotionally you should buy that. Most of the, I think it looks, I buy into it, I agree, but நானே calculate பண்ணி பார்த்தா better அப்படின்னு தோன்றதா இல்லையா? இல்ல நீங்க டோட்டலா if you don't buy into it, சார் இதெல்லாம் புரியல சார், அது வேற விஷயம். Then I cannot proceed further. I have to stay put and explain more. Everybody with me?
Yes, sir.
IOA, please type. So far, so good. IOA, Prashant.
Yes, sir.
Very good. And IOA பதில் கொடுக்கலையா சொல்லிட்டான். Thank you.
Yes, sir. சொல்லிருக்காங்க.
Okay, thanks. Now consider different set of weights. Okay, so this is our new correlation matrix, right? Theoretical variance covariance matrix. From there, I can even get to correlation matrix also. But anyway, this is what it is. Now let's calculate. Let's give a different type of weights like this. Okay, this is just playing with that and showing you, trying to show some result. Okay, the result is that the loadings are not unique, and yet you will get the same result or almost same result. Are you with me? So we have different. That's what I'm trying to show here. Different weights here. Again, the theoretical variances can be calculated like before. Now examine panel 14.1. Let's see panel 14.1. 14.1. Okay. Poor mark. Beautiful. IOA. IOA raise sum of weight should be equal to 1 for a variable. So some such conditions we need to make it 1, to make it unique, if that's what you are referring to. Okay, Prashant, did you see what the IOA raised the point? So we need some conditions. Sorry.
Yeah, I just saw.
Okay, so we need some condition like this, and I'm glad they went there quickly. We need some condition. We'll see what it is. Okay, and you are right. Now, so with that kind of approach, there is, if I put some restrictions on the weights, I'll be able to find the right loadings and I'll solve the problem. And what those restrictions you will see pretty soon.
So the answer is yes.
Yeah, go ahead.
For the question what Arun has asked.
Yeah, the answer is I just want to make sure, is that exactly what she's saying, or I'm going to say, is there something different? I don't know. I'm going to look at it right now in this example. Okay. But in general, we do need this kind of restriction. That's what I'm trying to impress on. Okay, some restriction we need so that it is unique. Okay. So here is the actual calculations. Here is the actual calculation using a statistical software. I can calculate this, the loadings, and then here is how we interpret it. The actual variance, observed variance of the original data in Y1 is this much, Y2 is this much, Y3 is this much. Total variance is this. The loadings for F1 are these things. We can find that out. I told you, right? The loadings can be found out, and we found out. Mathematically, we'll find that out. And I know now algorithm will polar. Another, I'm kind of committing less on some other things. I haven't gone to the algorithm, how it is done. இப்போ நான் சாஃப்ட்வேர் போட்டாக்க இது வருதுன்னு சொல்றேன் நான், right? I'm just saying if I put the software, I'll get the answers. BI1, so the fact, the loadings for F1 is this, loadings for F2 is this. So commonality, I would say commonality for this variable is communality for this variable is 9.83, and the specific variance is the remaining part. Do you see this one? This is very close to this one, this is very close to this one, this is very close to this one, because we use 2 loadings. If I take away this one, this will not be very close to this one as much as now it is. Are you with me?
Yes, sir.
So the idea is really an algorithm which provides this kind of solution to us, which splits the variance of Y1, Y2, Y3 with the same hidden factor F1, F2. With the same hidden, see, the beauty of this is that F1 and F2 is the same hidden factor that is playing a role here, playing a role here, playing a role here. But nonetheless, it is explaining the variance here, the variance in each of these variables through those the variance of the loadings, variance of the loading, the weights, variance of the loadings, which are the weights of the hidden dimensions. We are able to explain the total variance in each of these variables. A method like that, we can rely on it, isn't it? That's all I'm trying to say. Do you buy what I said? So F1, F2 is common for all. Yeah.
F1 and F2's impact on all variables?
Yeah, same dimension, but they have different weights. Same dimension F1, F2 only I'm using, but they have different weights for each of the original variable. But இது ஒன்றும் புதுசு இல்லையா, நம்ம ஏதோ பார்த்து எப்பவுமே இதான நம்ம பண்றோம்னு தோணும்.
But here we have got the value of F1, whatever values that is displayed here is the value of F1 or F1 into VI1.
This is only loadings, which is BIs. This is BI1s, BI2s. So the question is, what is F1? I think that's what you're trying to say. I mean, here this is not F1 times BI1, if that's what you were asking. No. This is just the loadings, BIs, beta I's or BIs.
Beta I's, yeah.
Okay, these are only loadings, okay? So the question is, I'm not saying the value of Y1 is this one. I'm saying the variance of Y1 is, the communality, because we saw that formula, right? The variance of Y1 is communality plus specific variance, isn't it? So I'm only talking about the variance here, explanation of the variance. Everybody understands?
Yes, sir.
Okay. So, so the question could be, என்ன சார் இது ஒரே தொந்தரவு பிடிச்ச வேலையா இருக்குது, F1, F2 தெரியல நமக்கு what it is, right? F1, F2 தெரியல. We know the loadings, okay, we understand there is a formula, we can figure it out, algorithm நம்ம கண்டுபிடிச்சிடலாம். F1, F2, beta is not கண்டுபிடிச்சிடலாம். The advantage is that that algorithm should explain in such a way that the total variance here is split into this communality plus the specific variance. Specific variance should go down as we increase the number of hidden dimensions. But what are these hidden dimensions? That question is there, still open, right? Okay, now hidden dimension is something that you are going to define based on how these weights are. Does that make sense? You are going to define a new name you are going to give. It's not just a name, that's all to you. So what does that mean? Here, finance is, based on what is heavily loaded, what is heavily discounted. What is heavily loaded or what is heavily discounted is going to help you to define the new dimension name. You need some name for the hidden dimension. So here it is heavily loaded on the finance side, but here if you look at it, marketing and policy are correlated. Okay, so this refers to more about numeracy. This refers to 2 and 3. Marketing and policy refers to at least the scores that were obtained from a particular marketing program is probably more about policies rather than what is called database marketing. Are you with me?
Yes, sir.
But isn't it nice that we solve the problem with fully interpretable answers, somehow digging into the hidden dimensions with the structure that the hidden dimension, the original variables are explainable with the latent variable called F1 and F2. Okay, through this structure, all comes down to this particular structure. What is that? One moment. Yeah, this structure. So we are pulling out the hidden dimensions as long as those hidden dimensions, and that's the assumption I'm explaining right now. As long as the hidden dimensions are linearly related to this original data, I know a way of pulling it out. That's what the factor analysis is all about. Okay. So let me see. Okay, so far so good.
Yes,
Now
sir.
you are getting now you are getting anxious about the algorithm. Show me the algorithm. Show me the algorithm. What is it? How is it? How is it? How is it? Right. So let's go there in a moment. So this is embedded in the full PA2 notes. Okay, don't worry about it. This whole document is embedded. Okay. So before I go and solve problems for you, let me address that issue of actually what happens in the matrix notation, which is any number of dimensions. Okay, so the point is, as before, we use a rotation method. Obviously, makes sense, right? Everybody, it's rotation and shifting the location and rotation. But the purpose is to work with the hidden dimensions, not with the original dimensions. That's the only difference. So if somebody asks you in an interview, what's the difference between PC and factor analysis? What would you say? Anybody?
BCA we use known variables, and for FA we use the hidden variables.
So if the interviewer asks you, I don't understand what is meant by hidden variable. Explain. I understand original variable. What is meant by hidden variable? And yeah. Anybody wants to try? Try. I mean, there is nothing wrong, right or wrong. It's just a matter of getting that out, committing to say something, and then checking it out. That's all. Okay.
Hidden sense, like unknown, they are unknown.
So maybe I'm just wondering. Maybe you can. So hidden, because you got to start with the idea that in certain applications, variables are measured with error, especially in talking about intelligence tests. Okay, that's easy example for me. There could be other applications, like talent management is another one. So when variables are measured with error, the relying on the original variables and doing the PCA will be error prone. So we structurally design a method. We structurally explicitly address the error in the observations through a model like what I showed you in a simple F1 F2 form. Agreed so far? And where F1 F2 are considered as the hidden variable. So how do we define the hidden variable? Finally, the weights, the loadings, where it is highly loaded versus loaded close to zero versus negatively loaded, helps us articulate the meaning of a hidden dimension. Are you so far so good? IOA, please.
Sir, hidden variables mean when the loadings
Hidden dimensions, hidden dimensions are a way of extracting the dimensions. The hidden dimensions are the dimensions which contribute to the variations in the original data. But we don't observe it. We observe it only through the articulation of the loadings or the weights, betas.
Okay, sir.
Okay. IYA, சத்யா கரெக்டுங்களா சொல்லுங்க. Yes, sir. Okay, good. Okay. So there are various methods of rotating it in such a way that we can get loadings for the for the original data, and I will come back to that. This is SAS output. I don't want to worry about that now. So I talked about this, explained this one, right? Did I? Oh, this is okay. So so this is the there are different rotation methods, different methods that use the non-unique. I told you right earlier, non-unique loadings, but they will all have consistent interpretations. Okay, so there is a method called Varimax. Okay, so what Varimax, there are many things. I'm not going to talk about a lot of things. I'll talk about only about Varimax. Varimax actually rotates the data in such a way that the resulting hidden dimensions are very perpendicular as much as possible. Resulting hidden dimensions are very perpendicular. Okay, which is what we want in general, right? But Varimax explicitly does it. But if you don't do that, you may not get the what is called the independent dimensions. Okay, they will have correlation. The F1 F2 will have correlation. We don't want that. So the Varimax rotation, in this case, Varimax rotation for the same data. But remember, I have to talk to you about a little bit about transformations there. Okay. So let me just tell you. Let me just tell you this information. It's very important. Two methods I will talk about. Edit. I don't know what's going on. Comment. Okay, let's see. No, not this one. So Varimax is one of them, and Quantimax is just to compare the these two methods. Okay, I want to talk about only two methods, and Varimax is very common anyway. Okay, so one moment. All right, so the Varimax rotation, the purpose is to find those loadings that maximize the variance of the squared loadings for each factor. Okay, maximize the variance of the squared loadings. So basically, you are maximizing the communality. On the other hand, so let me qualify the Varimax again. Varimax also helps you to detect factors that with reduced dimensions very directly. Okay, Varimax encourages the detection of factors, each of which is related to few variables. Quantimax, the another one, what is called Quantimax, seeks to maximize the variance of the squared loadings of each variable, but tends to produce factors with the high loadings for all variables. Okay, the weights are bigger here. That's all they're saying. Okay, the weights are bigger here. Here, the idea is to. Both the cases. No, see. Remember, eventually, every method has to really maximize the variance of the squared loadings. Everybody agrees on that one, because your total variance is the loadings communality, which is the variances of the loadings, right? The squared values of the loadings. That's what communality is. Communality is, let me go back. I'm just recalling the formula for you. The variance is communality plus specific variance. So if you want to create a solution, it should explain the squared betas, the loadings. Any solution should maximize. Any solution should maximize the loadings, squared loadings. but small differences between how it is done subsequent to that or in the process is what differentiates the various criteria. Okay, so I'm saying Varimax is a method with very purpose is to make sure that the fact, I don't know, this seems to be somewhat it's not detection of variables, factors influencing all. So what I mean, it's a little bit difficult, so I'm trying to give you the right words, not repeating what they are saying here. So Varimax is what Varimax does is it gets a solution, which is the purpose is to maximize the explanation of the communality, maximize the explanation of the communality. Okay, and as much as possible in the process, reduce the common element that are there between each of the factors, which is what you want actually, so that's good in a way, right? There could be some small parts that the small parts that are overlapping between hidden dimensions. There could be some small parts, and it pulls out, it reduces that as much as possible at the same time. When you're confusing, I don't just hang in with me, because if I repeat this 2 or 3 times, it will sink in, I think, So on the other hand, Quantimax is just a comparison. We are not going to play this out too much. Comparison. On the other hand, because you need to know why there are different methods out there, right? That's the reason why I want to explain this. So in comparison, Quantimax, is a method that produces the hidden dimensions with high loadings for all variables. That's what the method results into. So when we do the applications, you'll be able to see that and appreciate that. Okay, what I'm saying. So again, the another thing is in terms of number of dimensions, you also have to think about number of what is called the number of factors, isn't it? You have to think about number of factors here too, which is what your number of like similar to number of PCAs, you have here a problem of number of hidden factors. So it's all where you want to cut it down. Okay, so now let's take another example. This is a data set about real estate data sets, prices and features of 100 residential real estate properties, which is a common example you use. We have been using it in our course, right? So here is area, lot size, number of rooms, number of bathrooms, and more. Okay, number of bathrooms. 4 variables are there. When we use in this particular data set, the factor loadings, again, we are talking about factor loadings here. There is a loading weight of 0.9 for area and 0.99, 0.87 here, 0.78, 0.17. And I want to ask you one question here. Okay, I want to ask you one question here. I am in a interesting territory. So are you guys with me so far? Or confusing irka? Confuse pannirukkana?
A little bit confusing.
Okay, little bit confusing because 2 things, I guess. One is why there are 2 different methods. I talked about Quantimax versus Varimax, right? Rotation, different rotations. That's one.
Yeah.
There is still an open question of what is meant by should we worry about uniqueness? This is what the uniqueness issue is, not there, right? If I use Quantimax, I get a different loads. If I use Varimax, I get a different loads. Okay, but consistently, it should solve the problem. But let's not worry about too much on consistency at this time. I am into an area which is I'm trying to control the lot of uncertainty, in the knowledge and in communication. I hope you understand that. Okay, so the one beautiful thing here is, take a look at this one. Beautiful thing here is that Whenever it is high here, it's not loaded much here. Whenever it's loaded high here, it's not loaded much here. So I get in two interpretation, Codimax versus Varimax. I said one of the method will try to make more and more perpendicular. If I can say the word more and more perpendicular, right? What is that? In this case, what do you think this method would be here? Of course, we don't. I mean, I will find out the data where it is. I'll have to look into that. Then maybe run it myself. Two different ways, and I don't know that it shows two different ways. I don't even know this. This is the first time I'm going up to all these things because you guys are awesome and ask me good questions, and I'm taking more time. But anyway, it's all worth it. So I will look for the data and do it. But here I'm saying, for me, it looks like Varimax. Okay, but I'm not able to locate this. That's why. So are you with me so far? At least you can. Oh yeah, I said it. Yes, thank you. Exactly. Prashant, are you with us?
Yes, sir.
Excellent. So now it's just a matter of coding. You do the coding, you can interpret it, you can solve the problems. Number of loadings you want to cut it out, use it, and interpretation of them, interpretation of the hidden dimensions, interpretation of factor analysis, complex problems where we are pulling out hidden dimensions into our into the representation of real world. Okay, isn't it cool? I think it's very cool, and I know the coolest part is you are all with me so far. Okay, after 1.5 hours. So can we take a break now and then come back and do some actual calculations, or maybe I think and close this one, and then we'll talk about a few other topics also before we. Oh, it's 2 hours we take. Okay, that's fine. Let's take 10 minutes. Is that okay?
Okay, sir.
Sir,
will we be able to finish by 8:15?
Oh, 8:15. But no time in 7:30.
7:30. Sir.
Okay. 1 hour முடிச்சிடலாமே அப்படின்னா 7:30 இல்ல half an hour, right? 8 no half an hour. Okay, let's do one thing. Completely broken, cannot hear anything. Oh, okay. First and foremost, I said super, you identified as Varimax. Okay, one thing. Second thing is we are talking about the time. I said take 10 minutes, but looks like he needs to go. Prashant needs to go. So let's finish. We are supposed to finish it at 8. Is that what it is? 8:30 time. I'm supposed to get. But you have some commitment. Okay. All right. So let's do this. We'll finish it in half an hour. Okay. And then we'll continue next week. Thank you. Give me 10 minutes break, please. Everybody take 10 minutes break. Thank you.
Yeah, sure, sir. Sure.
Resume. So I'm starting with the second part, and I'm introducing you to cluster analysis in this today. We will do a couple of examples of factor analysis in the lab session. Now, cluster analysis is another type of unsupervised algorithm where we don't have outcome, but we want to find out the reduced data-based, information-rich, reduced database, dimension-based but information rich classifications. That's what clustering is all about. Okay. So this is we are trying to find the classes. That was not the case when actually you have classes and you want to predict, which is what logistic regression is. Okay. All right. So I want to talk to you a few, there are different methods there. But each of these methods have different logic. One of them is, for example, here, is that the distance among the groups which are in the closer neighborhood, the observations which are in the closer neighborhood will form a cluster if it's too far away from another cluster of observations where the intercluster distance is less than the between cluster distance. Get it? It's a logic. The logic here is whatever the intercluster distance here you have. Okay, there is a distance here, distance here, distance here, distance here, distance here, distance here, distance here. There is NC2 ways you can calculate the distance, right? And the average of that, you take the average of this, and then you take the distance from the midpoint, some kind of average of all the observations here, to the midpoint, some kind of average of all the points here. If this distance is too far compared to this one, the average distance among themselves, definitely this refers to a different group than this one. Do you buy that? Do you agree? Yeah, good. Very simple, very basic, right? And the other one is what is called the hierarchical clustering. And we are going to do all this. I'm just talking to you some logical steps here. Okay, we will do a lot more detailed work, immersive work. Okay. The other one is I'm trying to group this is the whole population observation. Remember that. Here the whole population observation refers to 3, 6, 7, 10, 13, 16, 16, 19, 20, 23 observation is population here. Okay. But here we are talking about only the, let's say, 4 observations here. So we want to see, because how close 2 observations are is fundamental to understanding the clustering. But the problem is, not the problem. The problem can be solved if you say that, well, I will keep on looking for the observation which are closer distance, and then next distance, and then the next distance, and so on. Okay. So, for example, in this case, you can say this is either closer or this closer. Now, visually, I'm saying right now. Okay, visually, you can say these are 2 are closer. Next one is this one, and the next one is, combine this one, next combine this one, and the next combine this one. What I'm saying is the closest ones are these 2. Start there. The closest ones are these 2. And then the next closest one to this cluster is this one compared to this one. Okay. And then finally, once you have this cluster of 3 observations identified in a sequential process, what we call as a hierarchical process, then finally P1 is considered as part of the whole cluster. So what we are saying is sequentially we are trying to find out who is the next closest member. In this case, P2 is closer, because if you compare the distance between P3 and P4 and P2 and P3, so we say that P2 and P3 are the lowest, so first combines these 2. And then once I combine this one among this, in this cluster collection, is this too far or is this too far? This is too far, so next one is this. And given this one, the final point is added to this. Okay. Now, this the way how we define the distance, between points and between a new point and the already formed cluster, between points and how we define the new point distance between the new point and the already defined cluster defines different types of hierarchical clustering. So far, so good. I think it's a little bit confusing, but I do want to say that that I'm trying to give you why there could be different types of hierarchical clustering. Are you with me?
Yes, sir.
Okay, cool. Now, and once you the beauty of hierarchical clustering is that you can arrange them in a graphical form like this. Okay, see P2 and P3 are closer, so it starts, they are connected at that height. In other words, whatever is the distance between this, that is the height here. Okay, but P2, P3 are connected to P4 by the time the distance is defined as, at this level, the distance is defined at this level. Okay, and finally P1 is part of the whole hierarchy, whole group, whole class. Now, the other way to do so the graphical representation is called dendrogram, and that is is commonly used for hierarchical clustering. So what I want to do is I want to finish. There are two clusters I talked about, right? Hierarchical clustering, and then the other one is what is called this one is what is called the it's not coming. Okay, so this one is what we will call as k-means clustering, and this one is hierarchical clustering. So let me finish today k-means clustering, and we'll call it a day because I have only another 7-10 minutes. Okay. So that in the k-mean clustering, it's an algorithmic method that will help you to find the clusters. So the problem is, we have here 8 points. A1 is 2, 10, that is this point. A2 is 2, 5, that is this point. A3 is 8, 4, that is this point, and so on. They are graphically represented there. Okay. So the idea of k-means is that you got to know how many clusters you want to find. You want to predefine that. You want to know how many clusters need to be found. So let's say that we want to find 3 clusters here. Okay. And if that's the case, randomly start anywhere. So I'm saying randomly we started C1, C2, C3 here. It could be C1 here, C2 here, C3 here. Doesn't matter. Okay. C1, C2, C3 here. And once you have randomly selected points, I think it is here. Okay. We can use a type of distance. I'm going to use what is called the Manhattan distance. There are two, you already know one distance, what is called the Euclidean distance. Do you agree with me? Do you all know that you already know Euclidean distance? You commonly use that. Okay. But I'm going to use, for simplicity, for another possibility, I'm going to use what is called the Manhattan distance. What does Manhattan distance mean? So it is of this type. Usually in Manhattan, New York City, these are all perpendicular streets. Okay. So if you want to go here, let's say, I'll make it bigger. If you want to go here, the only way to go here from here is you have to go in one axis, and then you have to go on the other axis. The other axis distance plus this axis distance is total distance from here to here. Do you get it? Please say yes. Okay, cool. So we will use that kind of distance, okay, to define clusters. Is that the only way to do? No, but I'm going to do it today in this class using that method. So what we are saying is, I have known these center points for 3. I've decided to do 3 clusters, and I have selected randomly these 3 points. I calculate the Manhattan distance for each of the other points from this. And whatever is closest to that, I will consider that belongs to that particular cluster, centered point, particular clustered center point. So I have 2, 10. So the distance between 2, 10 to 2, 10 is 0. Okay, but 2, 10 to 2, 5 is 5 units. Do you buy that? Using this, very simple, isn't it? Yes.
Yes, sir.
Okay, cool. And the distance between 2, 10 and 8, 4 is 12. Do you buy that? Because 2 minus 8 is 6, 10 minus 4 is 6, so it's 12. So I can fill up for the whole collection of The whole cell I can fill up. Do you agree with that one? Do you agree with me?
Yes, sir.
Okay.
Yes, sir.
So I have done this for 059. I mean, I found this value 059. This is 564. And between these two rows, based on these rows information, this is the distance. Anyway, we are calculating the distance between 2 comma 10 with respect to 2 comma 10. It's going to be 0. Okay, so that's not an issue at all. It doesn't matter. It's a plus 1. Nothing needs to be accomplished here. But anyway, I calculated that. But here, if you look at the 564, the lowest is 4. So what does this mean? This means A2 belongs to cluster 3. Do you buy that? It's the closest among 1 to 3, it's closest to 3. That's all I'm saying. So I can fill up the whole thing and identify what the clusters are. Agreed? Everybody?
Sir,
Sir,
I didn't get that.
Okay. No, what I'm saying is, so
how do we say the cluster?
Yeah. This is the calculated values, let's say. Everybody? IOA? Oh, yeah, she says yes. So we calculated these Manhattan distance. Do you agree? Do you understand, Prashant? These are all Manhattan distance. Okay. You know how to calculate also. Okay.
Yeah.
And these are all the calculated values. I don't have to worry about it because it's already. I'm trying to check here 2 comma 10. Where does it belong? It should belong to 2 comma 10. So it's a kind of trivial information. But look at this one. The minimum distance is 4. So I'm saying 2 comma 5 belongs to cluster 3. Here I look at it. Now the minimum distance is 7. I am saying 8.4, A3.83 belongs to cluster 2. In the same way here, 5.8. This is a kind of trivial information. Do you agree?
Yeah.
That's not an very extremely valuable information, but we just have to do it as a systematic way. This is a trivial shape. This is also trivial like that. The same points will be pretty much useless. I'm saying it's trivial information. I don't want to say useless. These are all trivial, and then like that, this one, right? This is trivial. Forget about these things. But rest of them I assigned them. Do you agree?
Yeah. Yes.
Cool. But now I know what are the points that belong to cluster 1, cluster 2, cluster 3. Now I calculate a new center. Understood? I calculate a new center, new averages. And based on that new average, I redo this one. Can you do me a favor? Work it out at home. What is the new center for cluster 1, cluster 2, cluster 3? See, earlier the old center was 2 comma 10, well-defined number, integers. Maybe it will be a fraction now, right? This is the center, this is the center, this is the center. But with these assigned values, calculate the new centers. This is why it's called k-mean clustering, okay? New averaged, okay? Averaged center. For that average center, redo this distance matrix again. And see this is changing or not. You repeat this until it is stable. That is called k-mean clustering. Did you get it?
Yes, sir.
Okay, cool. So the one small exercise you will do is recalculate the centers. Okay, can you do this? And by next week when I see you, and then make sure that you do it until it is done. What is meant by stopping rule here is that they don't change. The stopping rule is don't change. Until then, you have to keep on doing it. Mean of what? Mean of the observations, the points in the cluster. So in this case, there is only 1 point still. But here, the cluster 3 has this point, 2, 5, and 1, comma 2. The mean is 1, comma 3, 3.5. Agree? The mean of A to A7 is 1, 3.5. Agreed?
Yes, sir.
And use that new center to, you have to calculate for each of the clusters. And use the new centers to find new distance matrix and then reassign these numbers. So, do it until the clusters don't change. And in this example, it won't change after second time. So your second time will be the right answer. Are you with me?
Yes, sir.
Excellent. I know you are in a hurry, so finish it now and do this exercise. We will do more examples on factor analysis and cluster analysis also. There are more deeper cluster analysis works to do. Okay, just I introduced you, came in clustering today. Any questions before we call it night?
No, sir. I'll be having questions only when I try to calculate the new centers.
Okay, good. That's fine. That's fine. Just try. Okay. Thank you. IOA, any questions? Okay. No, sir. Okay. All right, folks. I appreciate your patience, especially today. Not. Sorry about that. All right. Have a nice evening. Good night.
Yes, sir. Sir?
Yeah.
When will you post this recorded session?
I'll do it. I'll do it tonight before I go to bed. Okay, which means give me 1 or 2 hours maximum. The thing is now, one thing which is still confusing is now I didn't answer the question. I didn't answer the question. Can we make it unique? Okay.
Yeah.
It doesn't matter. That is where the different rotation schemes come into play. The different rotation methods come into play. So it's a matter of choice rather than trying to get one value. Okay. Even though the ideas that IOA pointed out are the standard things people use it. Did I answer your question correctly now? IOA, and you didn't ask the question. You actually gave the answer, and I was tending to go in that direction. And I'm telling you now, there is no unique. Okay, there is no unique values there. There are different methods in return coming out with the different methods. Okay, and different methods have different tendencies to give you the interpretations. Okay, and different help in interpretations. And we'll see a couple of examples, probably two examples, the differences, and it should be okay with you. I hope this clarifies that. இன்னும் கன்ஃபியூசிங்கா தான் இருக்கா பிரசாந்த்?
அது மறுபடியும் ஒரு வாட்டி பார்த்துட்டு பண்ணதான் சார்.
Yeah. Right. Okay.
அடுத்த வாரம் நான் கேட்கிறேன்.
No problem. All right, folks. Take care. Good night.
Yes, sir.